Games. We love to play them, and sometimes we even like watching other people play them, whether it's chess, soccer, or even Overwatch. But why? What's the point? Well, in general, we get some kind of reward for playing games, maybe having fun with friends, being in better shape, or possibly even earning in-game experience. And the more we play these games, the better we tend to get. And as we get better and better, we start to see more and more rewards for playing them. However, not everyone can be a professional athlete or a chess grandmaster, including myself. And that's one of the reasons why I started looking into reinforcement learning, which is the type of machine learning that essentially lets computers learn how to do things on their own, playing games included. In essence, reinforcement learning, or RL, is a system that works by maximizing reward over a series of many actions, learning to take better actions along the way. Now, as you may have noticed, that's pretty similar to how we learn. So when it comes to explaining RL, let's start off by using the analogy of a baby learning new things. A baby would start in a house, and then it proceeds to try everything. It'll smell, taste, and touch pretty much anything it can get its hands on. For every action that the baby takes, it will notice that certain actions lead to rewards, and others might lead to punishment. Over time, it'll start to maximize the actions that lead to reward, while minimizing the ones that lead to punishment. Now that pretty much covers the entire RL process, but there's a few key terms that we need to know, and a lot of them relate to the analogy I just gave you. First, you've got the agent, which in our analogy would be considered to be the baby. Next, you've got the environment, which would be the house in this example. The baby can then take actions, and then each action that the baby will take will result in a new state and a certain earned reward. Now, when you combine everything into one big process, you get something called the Markov decision process, which is just a cycle of constantly taking actions and receiving a new state and reward. Adding on just one more term, you've got the policy, which is how the agent decides to go from a state to taking a specific action. Now I get it. That was a lot to digest. So let's look at an example of how it's being used today. First off, developers at OpenAI have been able to get multiple agents to play hide and seek in a 3D environment, using tons of different strategies. These agents learned how to create their own shelters using various blocks, and they even managed to use ramps to get into the shelters as well. One thing that makes RL particularly special is that since there's no special incentive for any of the actions, sometimes agents can even break the games by learning new strategies, such as surfing on top of boxes. That's crazy. It's definitely not something that you'd expect a normal computer to be able to do. Let's move on to something that I made and delve a bit deeper into the details behind RL and some of the algorithms that I used to make it work. A good starting point that I thought would be pretty interesting to try out was making a maze game. So I made a relatively simple 9x9 grid, and the agent starts out in the top left-hand corner, and its goal is to get to the bottom right. Now you might notice that there are these certain black spots, and those are what I like to call pitfalls. Every time the agent goes there, it loses 25 points. Every general move it makes it lose 1 point, and for getting to the final goal, it gets 300. Now if it wasn't obvious, the agent can only go up, down, left, or right. So after I finished this, the environment was pretty much completed. So all that's left was an algorithm to tie everything together and get the agent to actually start learning. What I ended up choosing was something called QLearning, which is an extremely long formula that boils down to determining the best rewards for every possible state and action pair. For my environment specifically, there were 81 states because I used a 9x9 grid, and 4 possible actions being up, left, down, or right. So that's a total of 81 multiplied by 4 possible state and action pairs. QLearning creates a table with every single one of these pairs called a Q table. And the table's values are a result of factors like the current reward, expected future reward, and the current value already in the Q table. Based upon all of these values, the agent can choose actions based on each state and update the table with a newer Q value. Now, there are some extra points to the formula that I haven't covered here, but if you'd like to know a bit more about it, I wrote an article that should be linked in the description down below. But now you're probably wondering, how did my system actually work? Well, in my personal opinion, I'd say that it succeeded with flying colors. I gave it 10,000 tries through the maze with 300 attempts, and after about turn 5,000, it was able to find the perfect solution every single time, using the least amount of moves possible to get it to run well. And I admit it wasn't a very complex solution, and it only took my computer about 30 seconds to run through it, but that's still pretty crazy. That's faster than a lot of normal people would be able to navigate the maze in. Now, all things considered, RL can do so much more, and it even has applications in the real world. Right now, people are using RL to control autonomous vehicles and even robots. Who knows? Within the next 5 to 10 years, we could have our own personal reinforcement learning robotic assistants. Well, see you next time, and thanks.